I'll try. Right here, right in my face. All right, let's do it. So OSXCollector is an automated forensics evidence and collection and analysis toolkit for OSX. So brief synopsis of what we're talking about. Who am I? What was the problem I was solving? Details on forensics collection and analysis, and then the part where you all applaud wildly. Early applause, I love it. So yeah, this is me. My job, I work at Yelp managing our security team. So it's a mix of application security, security infrastructure, incident detection and response. In the past, I've worked, managing Yelp's mobile applications development team and our internationalization team. And in the way back past, I wrote stuff like RDP and Xbox 360 and stuff at Microsoft that, I haven't seen a Windows machine in years. So it must be in use somewhere, but not here. But really, my job, it's protecting this. Yelp's a pretty big corporation nowadays. We have employees in 29 countries. We have millions and millions of people using our web apps, our mobile apps. My PR team, they tell me I have to show this slide so that you understand that you should go apply for a job there. That's not what I'm really here to tell you. If you look at that and say, okay, how do I want to defend that? How do I want to defend all of those employees that make that happen? That's a little bit about what we're talking about and kind of sets the scale for when we say, hey, let's not have malware, we're saying let's not have malware in 29 countries with all the employees it takes to do millions of clicks and things. So it's an interesting challenge. There's a bunch of other people here from the Yelp team who are working with me and have done work on this project. So yeah, the problem, defending against malware. So this is your typical diagram of a corporate network as far as I'm concerned. It's like, cool, corporate network, look at it. Do you know what's going on? Me neither. Cool. And then there's the security view of your corporate network. It's like pew, 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 everywhere there's fires burning up. What's that DNS thing going on? And why do they have that kernel extension? And fuck, there's malware again. And look at that new account. What's going on? Why are they calling out? Great, cool, swell. And it's now our job to say don't worry about it. We got it handled. It's cool. We'll take care of it. So this is our sort of view of the world. And we came from this view of the world and we said hey, I notice a lot of malware. Seems like OSX has got some malware. Not everybody's convinced OSX has malware. Last time I gave this talk, some guy was like, cool, you're going to talk about OSX and malware. I wonder if there's malware on OSX. You think so? OSX has shit tons of malware. If you haven't seen it yet, that's because it's on your machine and you're not looking. It's there. So we definitely saw it as soon as we started looking. And we were like, wow, look, tons of malware. And we were like, hey, let's prevent this malware. Malware in our corporation, bad shit, we don't want it. Let's prevent it. And so OSXCollector is sort of the first tool we came up with for how are we keeping malware out of our corporate environment. It works just as well if you have some non-corporate environment. I recommend you do. We couldn't really figure out where the malware came from, and so we weren't really successful at preventing it. And so OSXCollector was about prevent the malware. Hypothetically, if Iran had malware, we would want to know about it and say, hey, let's take action to stop Iran from spreading malware. Turns out they don't. So we got some people together. We built this tool. It's kind of cool. That's what we're here to talk about. Along the way, I'll give you some free malware prevention tips. These actually work. I actually took thousands and thousands of Macs and charted how did malware go? It goes poorly. But if you start to follow some of these things, they actually work. Most of these are not new. People have been saying these for a while now. They actually work. So click to play for Flash and Java, it just stops tons and tons of malware. Tons and tons of malware that we saw in the past before we did this were coming in these ways. But so now let's really get down to the heart of what we're talking about. So forensics collection. We use OSXCollector, a tool we built. We looked around and we said, oh, what can we use for forensic collection? And so we went onto Windows and we were like, oh, Redline from Mandiant, cool. We ran that and it runs and then you get all this data and then you read the data in their cool analyst tool. And you scratch your head a bunch and eventually you're like, oh, I think I might know what happened. And then you feel better about the whole incident. And we wanted to feel that way about OSX, but we weren't getting there. So we were like, oh, we don't feel good yet. So OSXCollector was an attempt to do that. There were some great tools already there. And we sort of went and kind of built something that kind of looked like some other tools that were out there, but worked very much for what we wanted to do on the collection side. It's all open source. It's been up there for a while. I'm really vain. Even if you don't like the talk, just star the GitHub page. It makes me feel better. Please. Yeah, so one of our first goals was we need to make collection really, really easy. So a lot of times, like, I buy these books, like these cool security books, and it's like, do analysis. And it's like, step 1, get an image of the entire machine and start playing with it. Except we're in 30 countries. We have all these different people. We don't have all the time in the world to take machines and put them on racks for months at a time while we do slow analysis. So, we needed something fast, something easy, something that an untrained technician could effectively bring onto a box and immediately start doing collection. So OSXCollector is pretty easy. It's one Python file for collection. That was a rule, a single file. It has no dependencies to be installed. Everything you need is in the operating system out of the box. That was important too. So basically, you could try to figure out, how will I get OSXCollector onto a box? And if you can do that through network, through USB, without spreading the malware that's already on the box, then you win, because you can basically just run it and go. So that was a big win. So we basically see in the output here a basic run. Sudo OSXCollector.py. You can pass in an ID, so it tags all the data with some incident ID. And that's about it. In this case, it wrote 35,000 lines of output. And we get it all in a nice tar gzip, and we're like, cool, we're moving forward. So all of the output of OSXCollector, when you untar gzip and whatever, right, it's all just JSON. And I actually and truly believe that JSON is kind of beautiful. Like, if you go to json.org, on the right side, there's this like beautiful drawing of how JSON works, and you're like, oh, I can understand that, as opposed to most things that I read. So I thought it was beautiful. And it's really easy to manipulate, and for us, it made good sense. It integrates with our tools. So this is sample output sort of showing us a single kernel extension. And we'll dive into what kind of stuff we collect in examples and how we sort of use that data. But remember, easy, beautiful JSON, we're going to keep using the tool chain to manipulate it. So let's talk about OSX a little bit. OSX stores lots of its data in SQLite DBs. Python is really good at dealing with SQLite DBs, so this was a win for us. I'm kind of ambivalent about SQLite, but whatever. One thing I found out, this is cool, researching the talk, I found out that the tagline for SQLite is small, fast, reliable, choose any 3. Kind of a hubris thing, I'm not sure they got there, but it's cool. But this is it. This is like the code you would need if you were writing Python or something to basically dump a table, a SQLite table. Sorry, take a SQLite DB file, dump all of the tables in it, and sort of get all the data. This is about it. So it's pretty damn simple, which was good. I liked it. The other thing OSX loves when we're storing data, and Forensics Collection is all about find all the data on the machine. OSX lovesplists. So plists are basically XML files. You see on the right-hand side, there's this XML file, ssh.plist, and it's just kind of describing data. Cool. Sometimes they're plain text. Sometimes they're binary. If they're binary, there's a command line tool, plist buddy. It will like print out a plist as a sort of JSON-y-like thing, not the XML, not real JSON, something else. Anyway, it's cool. It's a free tool. It works. So we use Python code to read through all these plists and kind of see what's going on. One thing I want to point out is a lot of this forensics collection stuff, not everybody knows about it. There's some really great places to learn more. Sarah Edwards is a researcher. I am Evil Twin on Twitter. I'd say 95% of what this tool does is coming directly out of reading her presentations and pestering her at events like this, and then figuring out how can we automate this stuff. So we automated reading a lot of plists because they had a lot of data, which made sense to us. So OSXCollector uses this Python class foundation to read plists, this package actually. And all it is a nice wrapper around Objective-C that the operating system is exposing to us. So the operating system exposes all these nice system calls. If you're an Objective-C developer, like go buck wild, go just start calling all them. If you're on Python, you like start scratching your head, then you stumble on Foundation. If you've written Objective-C, you will immediately notice, oh, damn. You will immediately notice how everything that you do in Foundation looks a lot like Objective-C. No Python developer in their right mind would make a function name that long, but Objective-C, that's like primo how to do it. So it's really useful. It just gets you at the system. So we're not writing compiled code. It's easy for us to do this, but we have a lot of power. Anything Foundation can get at, we can get at. And then it gets one step better. So it turns out, like, yeah, some stuff's not in Foundation. And that was problematic because there was stuff we wanted to know. So we said, okay, stuff's not in Foundation. We can't get at it. Fuck it, we'll figure it out. And so it turns out that, you know, in Python, you can just basically load libraries. And, you know, Python comes with this obj-C and C-type, you know, most, on OS X at least, you know, you have obj-C and C-type packages, which let you basically just call native code, whatever native code you want. If you can figure it out, you can call it. This is an example of calling an string with UTF-8, which is like a constructor for an Objective-C string. It's kind of messy. If you understand Objective-C, it's not so messy. But this basically meant at this point, with this single file, we could call anything on the system, which was kind of the goal of the whole thing. So now we can collect SQLite DBs, we can collectplists, we can call any system API that we want. That's kind of cool. We can start collecting lots of information at this point. So what do we collect? That's a pretty good question. And we kind of have this trade-off, like we could go across the whole file system, collect everything. It would take forever. Then in the case where it's like a false positive alert, we'd like have someone's machine in collection for 3 days and they'd be real pissed off. And then we'd be like, sorry, yeah, man, your machine's fine. It was just a mistake. So we're kind of careful about what do we collect, what do we not collect, and how much time we spend on that. So common thing that we look at is different kinds of files, applications, kernel extensions, downloads. When you're trying to figure out how did an infection happen, these are probably things you're going to be looking at. So back to our original example here of a kernel extension. We basically collect a bunch of stuff for all these files, right? We want to know the path of the file. We hash the hell out of the file, get a bunch of hashes for it, get the collection, the creation time, the modified time. We just try to get a bunch of information that we're going to want to look at later. And it's common across all these different kinds of files. Extended attributes, we get the signature chain, who signed this binary. One thing we do for times is we normalize them all to human readable times. So on OS X, in general, I'd say there's about 5 different ways that timestamps represent real times. And you sort of, if you're doing forensic collection, have no idea, like, what timestamp format is this plist going to use? So OSXCollector does a decent job of figuring out, like, I figured it out for you. Here's the timestamp. Don't sweat it. It basically works. If it doesn't work, open an issue on the GitHub. That'll help us out. So timestamps are normalized. Timestamps are incredibly important in establishing timelines when you're looking at a box. Yeah, we grab hashes. Hashes are still useful. Antivirus is not completely... we actually normalize them to the time zone of where the collection is happening, I think. I mean, it couldn't be normalized to UTC. It's like a one-line change. I mean, so we could fix something. I don't know. Yeah. It may be UTC. I can't remember. But yeah, they all get normalized the same way through the same one line of normalization. So if you're not into it, totally change it. So hashes, still valuable, still find shit. Lots of people say, oh, that's not real, that doesn't exist. You can't find problems with hashes. If you have hashes for stuff that you couldn't find before, now you can use those hashes to go find things. If you have 5,000 Macs and one of them gets infected with something you've never seen before, maybe some of the other ones are going to have the same hash. So hashes, we collect those. I think it's defense in depth. Yeah, all right. So what else do we collect? Quarantines. So quarantines are really cool in looking at how did infections happen on a machine. Quarantines are basically that thing that gives the OS enough information to be like, you downloaded Firefox from the internet. Are you sure that's okay? It's like, yeah, I get it. I downloaded stuff from the internet. But it turns out these are useful because they're basically tracking all of the downloads you made from the internet that resulted in someone trying to launch a program. And so, you know, this is a simple example. It says, like, Google Chrome downloaded Alfred, and I know about it. It happened at this timestamp. Cool. So if you're trying to figure out, like, how did this weird DMG get onto the machine? Okay, cool. It's in the quarantines probably, and that's just some plist, and we just converted it to some JSON, and the whole world gets a little happier. We collect startup items. So when you boot, lots of shit happens. All that shit that's happening while you boot is generally running in a highly privileged context, like root. So bad guys, they like to be there because then they're running as root. They're running every time you launch a box. They're running before you get a shell, after you reboot the box. So all that together means, like, yeah, startup items, good shit to invade. Yeah, so I basically just said whatever this thing says. But this is basically, some details about an SSH plist that has to do with key generation, which is cool, because, let's look at that. One interesting thing with OSX is it does not care if your startups are signed. So signed startups, if a binary is signed, then cryptographically, we're saying somebody has kind of looked at this and said it was cool. So in OSX, if something is signed, the operating system will verify it and be like, yo, this is good because it's signed. This is bad because it's signed but doesn't match. What it doesn't care about is if things are unsigned. Then it'll just say, like, cool, it's unsigned. It definitely didn't fail a signature check. Let's keep going. We kind of do care, so we collect that information. If you're interested in, like, could someone change the entropy in SSH key generation on your box, and would you notice it? Probably, because there's no signature on the binaries helping you do that. Oh well. So on to another section, malware prevention technique number 2, use an ad blocker. Can't stress this enough. It actually works. Yes, I'm from Yelp. Yes, this is how we get our revenue. What I suggest is AdBlock Pro, and then you add us to your whitelist. And then that allows everyone in the room to keep winning. Take it for what you will. Yeah, so forensics collection. We've basically now got this big hunkin' bunch of JSON describing a bunch of things going on the box. Great, that's cool. We have this data. It's not really fun to collect that data manually, but now we have it. Now sort of we can go on to analysis, which might be more interesting, it turns out. So forensic collection is hard. Forensic analysis is fun. It's like a little bit of science, a little bit of art. You're like telling a story. Oh, I get it. The user did this, and then that, and then this, and then they were fucked. It's like, okay, cool, I can get it. So I enjoy this part a lot. But the truth of the matter is, like, it takes hours and hours to do analysis, and that's how we started. We built OSXCollector because there was no good collection tool for us. And then we started doing analysis by hand, and we were so pleased with ourselves. We went from like 5 days to figure out what happened to 4 hours to figure out what happened by doing manual analysis, down to like just run some tools and let them tell you what happened. So we'll kind of walk you through that kind of chain of events here and some of the automated analysis. But first, manual analysis. Like, manual analysis works pretty good on this output. Like, you splat out the JSON, you grep a time window. It turns out, like, if you have some alert that fired, right? Like, hey, I noticed at this time this box did something really arbitrarily weird. I don't like it. So then we go grab that box. We do a little forensics on it. We go OSXCollector to grab up the data. And then we're like, yeah, now we can do some analysis. Grepping that time window for the events that happened. Often, it's pretty explainable. You see, like, in the list of every application installed that ever happened, an application installed that you've never heard of in that time frame. It's kind of like, oh, I get it. That application's bad. Sometimes, right? We can look at URLs in a time window. So there's this tool we use all the time, JQ. It's sort of hidden in the middle of one of these lines here. JQ is really awesome. It just greps and parses and transforms JSON data. And so we use it all the time to sort of explore and be like, what's in this data? What should we do? Data from OSXCollector, data from Elasticsearch, whatever data you have that's in JSON format, you can use it. If your data is not in JSON format, I recommend thinking about that and then changing it and then using these tools. So we can basically grep out whatever we want out of this data, and we often find like what's going on. You have a keyword, go grep it, see what happened, cool. But it's slow. It's still like 4 or 5 hours to root cause things mostly at this point. So then we went for like, let's just automate the whole fucking thing. We kind of knew what we were doing. We've been doing it for a while. so we automated it. It's a little hard to see, but basically, we now run generally one command, and then it prints out some very readable output. This is just a small snippet of it. But this is just saying like, yo, here's some like activity going on, quarantines and shit, from domains that OpenDNS said were bad. Like, why'd you go there? They're bad. So like, cool. If you see that, you get an immediate sense of like a quarantine. They downloaded something from a domain that somebody already knew was bad. It's probably fucked. It's not always so simple, but getting this really sort of easily readable summary of analysis was what we were looking for. Some stuff points out in the analysis like, okay, bad thing happened, I know about it, we're done. Other stuff points out like, hey, fishy thing happened, I don't know, you think about it more and figure out what the answer is. So we built this tool chain for OSXCollector analysis, and it's all with the collector, open sourced. And basically, we have this pipe and filter model where we can chain up all these different filters together. And each filter sort of does one thing with the data. And we say, okay, cool, we have some data. Hey, filter, do one thing. So like this first filter that we're talking about, it finds domains. It's like, is there a domain in this data? Yes, no, cool, whatever. And if it finds a domain in the data, it just adds another key to the JSON saying like, yo, here's the domains I found, cool. Cool. So we'll walk through sort of like what is the flow, or roughly the flow, that we do in this simple analysis, that we chain together all this crap for like amazing automated results. Woo! Yeah, so the find domains filter is sort of the first one. And yeah, I already kind of blew it because I told you, basically, if it sees a domain, it adds it to this output key, OSXCollector domains. It doesn't really matter where the domain is that it sees it, right? If it's in like the key of some JSON, if it's in the value, if there's some string and it's like an URL and that URL has a query param that's another URL or whatever, it does a pretty good job of finding all of it. And that's all we're trying to do. Like, yo, could you tell me the domains that are involved? And whenever we see subdomains, we add those, and then we also stem them down to the base domain, because when we look up domains later, maybe it's a new subdomain, nobody knows about it. Better just to say like, oh yeah, biz.yelp.com, that's also like yelp.com. Sometimes that's helpful. Yeah, and so then the next thing we talk about, like blacklists. Blacklists are super important. Whitelists work the same way. Whitelists are super important. What's the stuff you already know is shitty? Just give up. Be like, yep, that's a bad thing that happened. We know about it. We're done. Or I don't care about this data, so let's not look at it anymore as we start doing more expensive looks. So OSXCollector has a blacklist filter. It can basically match whatever you want. File hashes, parts of file names, domain names. It has some special smarts. If you tell it, hey, this is a blacklist of domain names, it kind of turns them into regexes, so it really finds domain names, which is cool. It also sort of has an idea where you can tell it, hey, these are bits of terms or fields, and you can basically match whatever you want. You can do regexes, you can do exact matches, and so that's great. So this simple example, right? Evil.com is here. We go and ask what domains are there. It says evil.com. Then we pass that on to the blacklist filter, and it's like, oh, evil.com is in our domain blacklist. Evil.com. I wish I owned that. That would be a fun domain. More likely, I would get streaminghockey.com. Turns out everybody wants to stream hockey, and it's all malware. Yeah, any domain at all with like free or download or sports bet in it is malware. That domain hosts malware. Canonical example being downloads.cnet.com. It's all malware. So this heuristic has proven very, very effective. I would recommend not going to those domains. So we can do a bunch of more stuff with this data, and we want to, because what we've done so far wouldn't tell you that much. One thing we do is we'll talk about what we do with some OpenDNS stuff, because they were really gracious to host us all here, and thank you, OpenDNS. Yeah, so we ask OpenDNS, hey, what are their domains related to the domains in this output? So OpenDNS is cool. They kind of know that. They know like not just like, hey, tell me about this domain, but they observe in time and space sort of what's going on with your DNS traffic or other people's, and tell you like this domain is related to that domain. And so it's like, you judge by the company you keep. We see a lot of times some event. Hey, this machine called out to this IP, did something weird, looks fucked up, we don't like that. So then we say, oh, bad. And then we go and look and we say, well, what's that IP? And we have no idea at all what that IP is, which is basically how malware works. They don't want you to know too much about what they're doing. They go and switch domains a lot. They go and switch IPs a lot. They try to shake shit up so you don't find them too quick. But so with OpenDNS's data, we look at like, okay, what are the domains related to this IP? And sometimes we get a hit. And then we look at what are the domains related to the domains that are related to this IP. And like we have a command line flag. You can like have as many generations as you want. But it actually turns out, really surprisingly to me, to tell you the truth, that like second generation related domains and IPs to some random C2 IP that no one's ever heard of, often like we find them in the output. And then we're like, oh, I get it. Here's the related domain where the infection started. Or here's part of, the IOC kill chain that we should be chasing down. It does work. And so this is really cool. Yeah, it works. And so we've got a bunch of, APIs and intelligence lookups that we do. We look up stuff with VirusTotal, and we kind of try to grade, like, if VirusTotal says something, maybe we trust it, maybe we don't. Shadow Server is another service where we can go send hashes and things and say, like, hey, what's with this? Shadow Server is cool, right? They have a list of hashes that aren't bad. So they're like, yeah, I know that file. It's some operating system file. Here's the path of it. Here's the name of it. This shit's not bad. This is really good as we start to do more and more expensive operations in the data, because we can just quickly filter those out and be like, yeah, not bad. Like, it's cool. We don't need to worry about it. So we like that a lot, and we use that. We look at domain reputation in VirusTotal and domain reputation in OpenDNS and all sorts of good stuff to try to figure out in this data with this intelligence feeds, what can we get? Cyber threat intelligence is like the big buzzword of 2015. Obama saw my presentation, gave his presentation. This is very important stuff. So OpenDNS, domain reputation filter, kind of the same thing. You can ask OpenDNS, yo, what do you know about evil.com? They have these categories, for example, where they say, like, this is the category of this domain. One of them is nuclear attack, which has never been in any of my data, but I like it a lot as a category. But then they can also give you all sorts of statistical scores, which you're free to interpret any way you want. And you can take some of those statistics and kind of build a model of, like, given what OpenDNS saw, like, do you care that someone went here or did something about this? Who knows? VirusTotal hash lookup, kind of the same thing again, right? We have a base class for API lookups. And so it takes all the heavy lifting out. It basically does rate limiting, does caching, does parallel issuing of requests to try to speed things up. So it's really easy to add new APIs. If you get really excited and go home and start hacking on this right away, go contribute new APIs, use the base class. It'll be really easy. I'll appreciate it. Malware prevention technique number 4. There is no free app to stream sports ball. Everyone who tries to stream NASCAR and hockey for free is getting malware. It's just a given. All right, so let's talk a little more about analysis, because I think I've blown through my time really fast. Yeah. So a few more things that we do, right? So browser history is pretty important. Most of your infections in a large corporation are coming in straight from browsing activities or from email, which is usually done in the browser nowadays. So OSXCollector goes through and it's like, yeah, I'll look at all the browser history, I'll sort it, I'll collate it. Basically, it's able to give you a view that looks a whole lot like the history tab in Chrome or Firefox. The cool thing is, in the SQLite DBs that are associated with browser history, there's more information than what you actually see in the history tab in Chrome, for example. So like Chrome knows, how did you get to this URL? Did you click a link? Was there a hidden pop-up? Were you in some sort of refer chain of 301s to some final destination? So there's cool stuff there. Like basically when you see hidden pop-up, it's always bad. Why did someone make a hidden pop-up? What a jerk. So you basically know, like, oh, that's the bad one, which is really kind of cool. A lot of these filters, we try to figure out sort of like, some filters are winnowing down information, sort of like the shadow server filter for good hashes. We get rid of a lot of information, and others are sort of trying to increase what we can look at. So we have a filter for finding files related, stuff related to files. So if you start out with a file, you know there's a bad file on the disk. Like, hey, I didn't want that file to be there. Then we want to kind of look and say, like, given this file name, can I find anything else related to this? Other files, downloads, domains, query strings, activity on the device, what's related to that file. And that basically helps us identify like more suspicious shit. Shit that initially did not look suspicious, but once we sort of already knew a hint, like, hey, anything related to invoice 337, that's already bad. Then it kind of gives us a better hint. So the filters are really pluggable. They're easy to sort of move between. You can pass data to them, individually, or chain them up in big chains. It has support for cool chaining things. And in our case, we sort of run one giant filter that chains most of the filters we have and prints out recommended next steps. So it says stuff like, hey, why don't we go blacklist this domain? And hey, pretty sure this file is like not good. Let's look for it from now on when we're looking for stuff. And then we, the humans, get to go take actions that them, the robots, told us to do, which I don't know why I like, but it's fun. So, yeah, sorry, I'm not good with time, but we went real fast. Hopefully you have compelling questions. So this is the wow, it's wonderful part, but a few more things before that. Yeah, I do work for a big company, and they do make me put slides in my presentations. This one's kind of cool, though. We have a lot of data. If you do any kind of data science stuff and you're interested in data science stuff, we publish these data sets. You can grab them. We have prizes for academics. If you, publish something using our data set, we give you money. If you present something using our data set, we give you money. We have big prizes. See terms and conditions. I did not just promise you any money at all. But we have this data set. Go check out the data set challenge if you want to know more. So I would love to know if people use this tool. So 500 some odd people have started. Like 4 of them have reached out to me. I love them. So if you use it, let me know. Let me know about it. If you're looking to learn more, these are, I put hashtags in here. These are hashtags where like I use to go learn more because I want to learn more. And that's my dog Molly. Yeah, and then that's case. And what questions could I answer for you? Hi. So you rely on Shadow Server to know what's in OSX versions. The question was, so hey, you rely on Shadow Server to try to know what's in OSX versions of patches? Yeah, we use it as a guide. It's helpful. I wouldn't say everything's there, and I wouldn't say it's always correct, but it's helpful. We explored quickly a NIST database that sort of has the hashes for every file they can find. I couldn't really figure out how to use that thing because it literally had the hashes for every file. So it was like no quality judgment being made. It was just like, yeah, that file exists too. What do we do about virtual machines running on the Mac? Yeah. We basically go like, yeah, virtual machines. Shit. So, honestly though, like your virtual machine, it calls out generally through your network adapter and the network stack is shared. So we can see some activity, but it's pretty confusing. If you really try to do forensics from the host and try to figure out what happened in the virtual machine, you will not figure it out. That's not our user model too much. I'm sure there's better solutions. If you know, let me know. Hey, yeah.
So are you collecting host names as they're resolved during the runtime? I didn't know if I caught that. Like, so.
All right, and do you want this one for right now, or? Yeah, here. While he's working on this one.
Hey, so the question was, do we collect host names as as resolutions are happening? So this tool is purely for forensics after something else has alerted. So we're definitely looking at network streams and creating alerts and then saying, now that we have an alert, what should we do about it? That's when we go to forensics. Hi. So what causes us to start running this tool? It's sort of the Death Star view of the network. It's like whatever alerting systems we have in place, so host endpoint monitoring, network monitoring, log analysis, whatever we've got in place, and we're sort of always trying to add more things as sort of ingress into our alerting pipeline. Alerts come in, we evaluate them at the point that we're like, yo, that box is bad, something is weird, I can't explain it, I feel funny. Then we want to go do this analysis. In our case, we actually try to automate most all of that decision making. So we aggregate all the alerts from different sources that we can. We put them all together. We have some smarts to try to analyze those things on a case-by-case basis and make decisions. Then usually our automated tools go and cut tickets for us and email users and alert the help desk and call out the dogs and all whatever. If you check out Yelp's GitHub, we have this other project from our security team called ElastAlert. It's an alerting system we built out of Elasticsearch. So we shove everything we can figure out into Elasticsearch and alert out of it. It has nothing to do with this talk, but I love to talk about that. So glad I got an opportunity. Do we do any live domain lookup in the analysis? The question was, do we do any live domain lookup, or is it all passive right now? Is that during analysis? So during analysis, it's actually it's way more close to live than I would like. When we do lookups of domains and when we try to say like, hey, in this forensic capture, there's this domain, what do we think about it? Most all of the data sources we use will tell us what they think right now. So if we're fast, we can learn what they think right now. Sometimes what they think right now is helpful because an attack started 12 hours ago and now they know about it. And sometimes we're effectively looking at old shit and our sources are like, nah, I don't care about that domain. But realistically, 3 months ago, when this thing started, that domain would have been more interesting to them. Anybody who's got threat information, if I can pass you a timestamp when I go and ask you about threat information, I want to do that. So then I could really say, what do you think right now? What do you think 3 months ago? What do you think when this shit actually happened? And I really wanted to know the answer. It's kind of tricky. I wish there was a slightly better answer. Are we tunneling that at all, or are we going out from our own network? As much as I don't want to answer this, we're mostly going out from our own network. So stop looking at what we're doing, because you would see us, I guess. That's kind of the risk, though, with all these third parties that you go to, right? You go and ask a third party, like, yo, can you give me some information? They're like, why do you want to know that? It draws conclusions for people. Have we found interesting attack vectors that we wouldn't expect? I think the answer is probably no. We haven't found interesting vectors we didn't expect. At times it's really interesting how successful some really stupid vectors are. So like browser extensions were one where I thought like, whatever, that's like not that interesting. Yeah, stuff gets in through browser extensions. I started reading up. There's like really interesting stuff if you read about like who buys old browser extensions with large populations of users. Because you make a decision once when you install an extension like, yeah, I trust this thing. And then it downloads and updates code randomly from some untrusted domain that, like they're all started by some kid in his dorm room, and then if they're successful, somebody buys them. And if you're a bad guy, just go buy successful domains or successful extensions and then put your bad shit out there. We have seen that. It's real. Hi. Do we collect browser history in OSXCollector, and do we grab all of the profiles? Yeah, so OSXCollector does collect browser history and more about your browsing experience, and it does it for all of the profiles in Chrome, Safari, and Firefox. Almost all of the collection we do, and the way OSX generally works is like a ton of shit is, hey, there's a system install of this, or a system version of this. And then there's a bunch of per user or per profile stuff. And so we go and collect the system stuff, and then we do it per profile. All the data gets tagged with like whose profile it was, so you can be like, hey, let's just go look at what Ivan was doing on this machine. Big tip, if there's a lot of profiles on the machine, something bad happened. It's not like 1980, you don't share the computer. Hey, yeah. About how long does the automated analysis take? It definitely depends on what's in the data and how much data we have. I think today it's an hour to 2 hours. I'm sort of looking at the back at some Yelpers to try to see if somebody nods their head. I don't know. It's like an hour to 2 hours. Sometimes it's like 5 minutes. Sometimes it's really long. But I think it's generally probably under an hour, sometimes up to 2 hours for an average sort of like, I had this computer for 18 months and kind of deal. Hi.
Does it only work when the system's running, or can you run it against like a cold disk image from a browser?
Yeah, so the question is, hey, can I run this against a cold disk image? Yeah, so if you pass -M and the path to a mounted image to the collector, it will go run against a mounted image. So yeah, totally possible, works pretty well. At times we do that. I've got like a Thunderbolt hard drive sled, and I will grab disks, image them, keep the images, or just mount the disks in the sled and go do analysis. How much do you miss when you do that? Very little. So this is mostly doing disk forensics, so you miss very little. Even the stuff that's not directly disk forensics, like system calls and stuff, are generally getting their information from the disk. And so generally it works. I actually don't know what you miss, but I bet there's something.
Like memory stuff, or you put on a process table, or like running on the system at the current time when you run it?
This is not doing any sort of memory forensics capture. It is not capturing the running processes on the system. Generally, this is being used in a situation where the machine is at least somewhat changed from when the alerts happened, if not very changed. It's probably stupid that we're not capturing the running processes anyway. Might want to do that later today.
There are some free memory capture tools you might look at.
Yeah, no, there's definitely free memory capture tools, and I think memory capture is super awesome. We just don't target it at all with this, but yeah, the volatility book, if anyone hasn't read that yet, it's like super dope. The Art of Memory Forensics by Andrew Case et al. The volatility people. They have so much great stuff on memory forensics. Other exciting questions? Thank you.
All right, just to let everyone know, the food